Okay, Assalamualaikum warahmatullahi wabarakatuh. So today is our last Webex conference for this academic year. And I see that there's nobody around, but anyway, today we are going to revise whatever that you have sit for your continuous exam so that you have some idea on how you should answer your final exam, because basically for the first question, even though it looks easy, but you need to really know on how to answer it. Okay, let's begin. Okay, these kind of questions will be there for your final exam. The first one will be something about with appropriate illustration, equation, if any. Give your comments on the truthfulness of the following statements. So basically what I'm going to show to you now is on how to answer this kind of questions. Okay, let's go to the first one, which is the first question in your continuous exam, which is crystal defect could be used to increase the conductivity of semiconductor. So the issue here is, just highlight it. Okay, so it's something about crystal defect. So you must answer something in relation to crystal defect and how crystal defect, whether it's possible or not possible to increase the conductivity of a semiconductor. So the thing is, I guess you know that doping is a form of crystal defect. But the thing is, but what is exactly doping if you would like to talk it in terms of crystal defect? So of course, yes, because basically most of you know that it's something to do with doping, and doping will increase the conductivity. But the thing is, what I've asked you is, you need to give your comments. When you just say doping, but what is your comment about doping that is able to increase the conductivity of the semiconductor? So your explanation, you should include explanation. So the crystal defect, dopant is being impurity substitution. But if you just say dopant only, but I would not know what is the function of doping in terms of, because I would like to know it in terms of crystal defect. So you must explain doping in terms of crystal defect, which is essentially impurity substitution. But the thing is, how do you visualize the impurity substitution? Because here I did say with your appropriate illustration. So you need to illustrate it. What does it mean by impurity substitution? So you need to have those pictures. You can use silicon because you have been learning about it all this while. So you just have some picture about pure silicon, and you know that for silicon, that's for it on the valence band, that's 4 for each silicon, isn't it? Okay, that's 4 for each in the valence band of a single silicon atom. And of course, to increase the conductivity, you knew that you need to increase the number of charge carriers, isn't it? So you need to illustrate in your this one, how you increase your charge carriers. Okay. So in order to do that, so you can just show whether you doped it with phosphorus, which will give you an extra electron. Yeah, where the extra electron will increase the conductivity of your semiconductor. And of course, you can also illustrate for another one, a P boron, where if you use this kind of illustration, you can clearly show that whenever you add boron means you are introducing holes in your semiconductor. And whereas this one, I mean, you can see clearly that it creates an extra electrons which is able to increase the conductivity of the semiconductor. So, the thing is, to answer this kind of question, you must make sure you look at the statements. What are the words that you need to tackle when answering the question? I mean, perhaps you could bring a highlighter like the one that I illustrate now, isn't it? So it's very clearly said that you need to answer it in terms of the crystal defect, which is essentially the impurity substitution, which is essentially what doping means. But the thing is, when you say doping, like I told you just now, it doesn't give the idea of the type of defect that has happened. Isn't it? You might get it right, of course. But the thing is, you lose marks because you didn't say it in a form of a type of crystal defect, because doping is not a crystal defect, but impurity substitution is a crystal defect. So it's best that you use the correct terms. Even though it's essentially this, but the thing is, the term to be used is impurity substitution. Okay. All right, so I hope you get the idea now, of how you should say it out. If you just say doping, it's also correct, but you need to have all this explanation. That your illustration must, really show what it means by to increase the conductivity. You cannot just choose any illustration, but it must, incongruent with whatever that the question is asking. Okay, so that's the first one. So let's see, how you are going to answer the next question. Okay, now the next question is, the end product of the silicon Zoroarsky technique is metal grade polysilicon. So you see now what essentially the word that you need to highlight is the end product of CZ, CZ technique is metal grade. The other word is polycrystal. So, how are you going to answer this kind of question? Well, first of all, do you know that what is the end product of the Zoroastrian technique? Is it metal grade? Of course it's not metal grade, isn't it? Because you are going to use the end product of Zoroastrian technique in order to grow in order to fabricate your devices. Of course, you don't want to have metal grade because in metal grade there are still impurities in it. So, what you need is the electronic grade, isn't it? But the thing is, do you want to have it in the form of polycrystal? Definitely not also, isn't it? Because polycrystal has a lot of grain boundaries which are bound to introduce defect in your devices. So, polycrystal is out, isn't it? I mean, think of it logically so that, slowly you are able to put in how to answer it out. Let's see, where's my nose? Okay. Let's see what color do I have it to be. So, metal grade is out. Polycrystal is out, isn't it? But where does this metal grade comes from? But where also this polycrystal comes from? In order for you to negate it, yeah? So, okay, so that's your metal grade silicon, okay? And that's your electronic grade polysilicon. Because at the stage of polysilicon, it should be already electronic grade. Because before Zoroastrian, you need to have it in a form of electronic grade already. Because it's just that at Zoroastrian, you just would like to change it from polycrystal, many crystal, into single crystal. So in order to get the metal grade, okay, in order to get this metal grade, you have to undergo the initial chemical purification. Isn't it? Where metal grade, you get it from this silicon oxide, from plus coal, and plus wood chips, carbon, and you heat it up to 1,800 degrees C to get your metal grade silicon. So metal grade is essentially the end product of the early initial chemical purification, the first step of it. The first grade that you get out of the silicon oxide. And the next stage is for you to get your electronic grade, but it's in the form of polycrystal. So polycrystal is in the form of electronic grade, not in the form of metal grade. Because from metal grade, you get it in the form of electronic grade, the purity of it. So, of course, you put your HCl, which you will get silicon tetrasilane. Tetra means 3, silane, you get it. And then, of course, you clean it up for the purification by fractional distillation So you get your pure silicon tetrasilane, and then you add hydrogen, then only you get your electronic grade polycrystal silicon. Okay. So you see that the end product of initial chemical purification is the electronic grade polysilicon. Okay. And of course, from this E-grade polycrystal, then you grow your bulk crystal. Yeah. You put it in your CZ crucible, then of course lastly you get your electronic grade silicon. So with this illustration, you have, you showed already to me that, yeah, by using this kind, so it's easier that I know, oh, you knew that metal grade comes from the initial step of the purification. And you knew that the polycrystal is in fact comes from the second part of the initial chemical purification, isn't it? And of course, yeah, the end product of your CZ technique is essentially your electronic grade. Yep. The keyword is bulk single crystal. So you see that, yeah, for the initial chemical purification, the end product is the electronic grade. Isn't it? And for the growth of the crystal is essentially taking it from this polycrystal into the bulk single crystal. So that's what it's all about. So initial chemical purification is from 99% impurities into metal grade, and then we go into electronic grade. Let's just use the highlighter, which is much easier. Okay, so it's from here to here. Yeah, it's about purification. So the first step is about purification, where you get your electronic grade. Now for the second step, yeah, it's about the growth, where it goes from polycrystal into bulk single crystal. So now you see where from each of the steps you see what is the function of it. So in order to answer this question, it's easier now, isn't it? So remember that in the first step is about purification, going from the outside into metal grade and then going into the electronic grade. But whereas for the second step is about the growth of the bulk single crystal, where from polycrystal we get it to the bulk single crystal, where the grade is essentially the same. Okay, pretty clear now, I hope. Okay, there we go. Okay, so the answer is no. The end product of CZ technique is is the electronic grade bulk single crystal. Yeah. So, like I've told you just now, yep, it's best that you answer it answer it according to the question that's been asked. Make sure you refer to the end product. What is it, the end product now? But you did show that the metal grade is where it's supposed to be, and the polycrystal is where it's supposed to be, and the last is this electronic grade bulk single crystal. You see, I did see, so to show that it's not a polycrystal, it is a bulk single crystal. To show that it's not metal grade, I did put the electronic grade. So, I mean, the question itself is already a guidance for you to whether you want to say it's yes or whether you want to say it's as a no. I mean, it guides you on how to answer it. So I hope you will use this kind of technique when you like to answer your final exam, because there's the first question is the question in this kind of technique. Okay, let's go to the next question and see how you're going to answer it. Okay, now the question is, the drift velocity of carriers will keep on increasing with electric field. So, how are you going to answer this one? I mean, it's something about the relationship between drift velocity and electric field. So, in this kind of question, it's best that you use a graph to illustrate the relationship. So, okay, so let's just do your highlighting work. So it's about drift velocity, and electric field. And it says will keep on increasing. Is it true? So we need to see the relationship between drift velocity and electric field. So the easiest way is to use the graph, isn't it? The drift versus electric field graph. But how would it look like? Okay. Of course, it's been shown in page 102. So if you can refer it there. But I've shown you here. But now, looking at this graph, you can see that the drift velocity versus your electric field is only increasing at this particular part only. So at that particular part, so the drift velocity increasing only at low electric field. But when at high field, especially when your drift velocity is approximately equal to your terminal velocity, then you find that at this particular time, the drift velocity is constant, or it can be called scattering limited velocity. So the thing is, you can see now that definitely the statement that says that the drift velocity of carriers will keep on increasing with electric field is partially true at low E, but not at high E field. Isn't it? Because at high E field is something called the hot carrier effect, where acting the E field will not increase the drift velocity, but it will be transferred to the lattice. So it will transfer to the lattice, then scattering will occur, which will limit the velocity, where the velocity will stay constant, especially for silicon and germanium kind of semiconductor. So now, from this graph, it's so easy you can see, isn't it? So, and then you can just say, no, VD increasing only at low E, and V drift is constant at higher E field. So the thing is, yeah, well, you can use the illustration since it's part of a graph, because you are using relationship. So this is the relationship between drift and electric field. Okay, like I told you just now, just use the statement to guide you in order to answer this kind of question. All right. Okay, let's go to the next question. Okay, so now is something about the carrier mobility can be known by measuring carrier diffusion coefficient at a known temperature. Okay, so the key word is mobility. Yep. By measuring carrier diffusion diffusion coefficient and a known temperature. So what comes to your mind when you talk about mobility, diffusion coefficient, and temperature? I think by now you should have know the relationship between these three important variables when you would like to talk about current density, isn't it? And you are going to use, and also you use this one in the PN junction, isn't it? In order for you to get the contact potential. So now, so what's the equation? What's the relationship? It's the Einstein equation, isn't it? Where the diffusion coefficient divided by your mobility is equals to KT divided by Q. And we know that our K is constant, which is the Boltzmann constant, and our Q is essentially the charge 1.6 times 10 to the power of a negative 19, which is a constant. So what's left now is the diffusion coefficient, U, and our T. So if our T is known, yeah, just have to take the different color. Okay, let's see, we know what T is, and then we measure our diffusion coefficient. Of course, it's possible for us to know our carrier mobility. So the thing is, you need to know this relationship. Of course, I mean, by now, since this is your final year, you are aware, you should be aware that equation, the relationship between one variable to another is very, very important. Okay, of course, now your answer is a yes. So, depends, yeah, the situation. All right. Okay, let's go to the next one. Okay, recombination in direct semiconductor occurs mainly at the trap levels in the band gap. Okay, let's see what are our keywords here. So our keyword is direct semiconductor trap levels in the band gap. Okay, trap level in the band gap. Recombination. Okay. So what should come in your mind? Of course, you must in your mind have a visualization of what a direct semiconductor is, isn't it? So is there any trap level in a direct semiconductor? Of course, there's no, isn't it? So how are you going to show it? So it's best that you use an illustration. Okay. Isn't it? So from the illustration, you can definitely see that there's no trap level in direct semiconductor. But where does this trap semiconductor comes from? Huh? Can't you just show it? If in indirect semiconductor, only you have this trap level, then you know. So you show that recombination trap level is indirect semiconductor. Run it. So indirect semiconductor trap level here. But if in indirect semiconductor, direct semiconductor, then there's no trap level. It's just direct transition. So it's easy if you illustrate it rather than you talk about it, because it can really, show straight away about the transition for the recombination. Okay. I hope by now you are able to answer this kind of question, because this is going to be the first question in your final exam, yeah? Which I think is on the 30th of May. All right. So let's go on to another type of question, which is basically more on the explanation. Now, how are you going to explain? Yeah, at times, things will get easy. Like this example, explain the formation of the energy gap in silicon. So the thing is, to explain the formation, basically it will be much easier if you use a diagram, isn't it? I mean, you can write it, but the thing is sometimes when you write, you can miss certain points. So it's best that you draw it. I mean, because pictures worth 1,000 words, so just draw it. And you knew that in silicon, there are 4 electrons in the there are 4 valence electrons in the silicon. 1, 2, 3, 4. I hope by now you know that it's the valence electrons are the ones that are active, that take part in all the conductivities. So when the valence electron of a single silicon atom, one silicon atom, a silicon atom, 1. So since there is 4, so 2 here is the S state. Let's have it. So this is the S state, because S has 2 level, energy level, and this one is the P state, since we have another extra 2 more electrons, so we have U here. But as there's more, when we bring these silicon atoms, a single silicon atom towards more atoms, so those 2 N states, 2 P states and 2 S states, it form continuous band. There's more here. Come nearer and nearer together more. As we bring more silicon atoms together, so all these energy states will form a continuous band here. But the thing is, when it reaches this actual atomic spacing, when we bring more and more of those silicon atoms together and we bring it much nearer to each other, so at this actual spacing, at this actual spacing, you see now that the 2N states over here has come down into these states. Because to optimize the distance between the atoms, then it's something that's called hybridization. That's the sp3 hybridization means they form new energy levels, where instead of it being at the P state, it formed this new energy level sp3. So where all of it will be in the valence band. So this initial single silicon atom, the 4 valence electron, has come to form energy state, a field energy state in the valence band. because at this particular, by doing this, they can optimize the distance between the atoms. So that's why it happens, this new energy level, sp3 hybridization, which is essentially the optimization of the distances, so that it can exist cohesively. So that's why we get our valence band. Whereas since our conduction band will be empty, because all of our valence band is now being in our, all our valence electrons are now in our valence band. Okay. So when it's far apart, it's, the relative spacing of the atoms, it's still in the continuous form, still in the 2n states and 2p states, and this one is 2s state, but up to actual atomic spacing, in order to optimize the distance between the atoms, they form new energy level, sp3, where all the valence electrons are now in the valence band, and there is no electron in the conduction band. And between these two bands, there's a band gap. There's no energy states at all. Okay, that's how you explain the formation of the energy band gap. So the trick is, so first you must say something about the initial. So you must say something about the single silicon atoms. Then you bring more atoms together, and then what happened to their energy states? What happened to their energy states? And then when you bring it to the actual spacing, and then what happened to all the electrons where it undergoes sp3 hybridization, like I told you just now. So that's why we get all this band gap. Empty conduction band and filled electron, filled valence band. So 1, okay, 2, okay, 2. So it's about distance and increase in the number of atoms. Okay. So increase in the relative spacing. So you have this continuous energy state, but still in the form of 2p and 2s, isn't it? But continuous energy level, isn't it? And 3 at the actual spacing. Okay, this hybridization occurs, which gives you this field state. Okay, all is being filled. B, 0 electron in the conduction band. And C, there's a band gap where there is no energy state at all. finite. So basically, these are the things that you should put in the explanation for the formation of the energy band gap in silicon. All right. Okay, look at it slowly. Then you can see that essentially these are the three explanation that you should include in your answer. Okay, so let's go to the next question, which is essentially calculation. Well, there should be calculation in your final exam, yeah? Silicon is doped with 10 to the power of 17 phosphorus atom per cm cubed at room temperature. Calculate the carrier concentrations. I guess most of you know how to look at the question because this is phosphorus. Phosphorus means phosphorus is bagi pas, isn't it? So phosphorus is N, isn't it? So N0 is equals to your number of dopant. And since the question asks for the carrier concentration, carrier concentration. So but not only you have to include N0, but you have also to calculate for your whole concentration. So whole concentration, I guess most of you know that you have to use the mass action law, which is essentially that one. Okay, I guess most of you know how to do this one already. So the next question is determine the position of the Fermi levels. Actually, there's two ways to do it, whether you would like to use the effective density of states equations or you can use the intrinsic concentration equation. So you have two ways of doing it. Okay, both are acceptable. So I guess you just use your natural log and you get the number, or you just use this one to get the number. So you look at this one, yeah. Of course, it should have different values because one is measuring the EF minus EI, and the other one is EC minus EF. So both are acceptable because we know that between E is in the middle and C, because we have already an indicator from where to measure, either from the E intrinsic or from the E conduction band edge. So both you can use. Yeah? Because the question doesn't specifically say that the position of the Fermi level according to relative to E intrinsic or whether it's relative to E conduction band edge. So you can just use either of the equations. Okay. So let's go to the next one. Yep. Explain the effect of continuous increase in temperature on the carrier concentration. Well, so continuous increase in temperature and carrier concentration. So the thing is, like just now, the drift velocity. To answer this kind of question, it's best that you use graph because it explains a lot of things. So you can just see here by the increasing in temperature, so there is a different changes in the charge carrier concentration. For the initial one, the ionization region, you have an increase in the number of carriers, but in the extrinsic region is constant, and at a higher temperature is the intrinsic region. So you can have it all, yeah, from this graph. Next, the mobility of charge carriers. So how does your temperature change with mobility of charge carriers? Of course, again, it's best that you use your graph. All right. There it is. Isn't it? Simple. Okay, let's go to the next one, which is essentially a trick question. It is asked for you to calculate the diffusion current density, and when the electric field is this one. But the thing is, diffusion current density is not being affected by electric field, isn't it? So what's the equation for the diffusion current density? So it's in the form of gradient of charge carriers with X. But the thing is, in our question, there's no gradient in your electron concentration, isn't it? Because you know that it's being doped by using 10 to the power of 17, and you know that your electron concentration is 10 to the power of 17, isn't it? It's a constant. So there's no gradient, because 0, of course. The diffusion current density is 0. It's not being affected by your electric field, unless it's drift, isn't it? Which is different. Okay, so this is a trick question. Lastly, in your exam, explain the technique used to determining the type of semiconductor. So the type of semiconductor, of course, you should by now know that you need to use the Hall effect, isn't it? So the Hall effect, you use the Hall effect measurement, where essentially the sign plus or minus of the Hall voltage, where the Hall voltage you measured it by putting your probe at the positive end and the negative end. Just put your voltage here across the semiconductor, where if you get your V Hall is positive, then your type of semiconductor is P-type. So that's all. Basically what your final exam were and your continuous exam. So basically I've shown to you how to answer this kind of questions. So I hope in the final exam you don't feel lost of how to answer the question. So just take a deep breath, breathe deeply, and answer your questions. All the best. I've illustrated to you the techniques on how to answer, which one should you graph, which one should use equation, and what are the key indicators in the statement that you can use as a guide for you, just in case you feel lost, you don't know where to start. So I've shown it to you just now. So all the best to you, and hope you will all pass with flying colors. Okay, thank you.